decided that we sort of to include that, just so like most of you already started. I'm just going to say a few words before Paul announces the main speaker. So this is the fourth in the Thalesians seminar. Last time, I don't know how many of you were here last time, but I can see a lot of familiar faces. We had Claudio Albanese from Imperial, and he gave a talk on GPUs and GPU computing for derivative pricing. And as a sort of follow-up from that, we're very lucky tonight to have some GPU hardware experts from Supermicro, and they're going to be giving a few sort of words on sort of new product ranges. So very exciting, and that will come after the main talk. So with that, I'll give you a talk.
Thank you very much, and I'm going to introduce our speaker today, who is a world-renowned expert on optimization. He has written numerous monographs. He's been an editor of numerous journals, and I'm just going to go through it. He's a professor of computational methods and operations research at Imperial College London. As an editor of Automatica, co-editor of Computational Management Science, advisor editor of Journal of Economic Dynamics and Control, and on the board of many other publications, and the author of 3 very big monographs on this subject. Co-presenting is Steve Zimmer, who is his PhD student, and we are very honoured by the presence today of Professor Berc Rustem of Imperial College. And could you all welcome our speakers? I mean, that would be.
Well, thank you, Paul. It's not going away. Okay, this is talk is mainly about robustness in its various forms and models. There are many views of robustness, and we'll try to touch upon some of them, in fact most of them this evening, although we will focus on one type of robustness mostly. And the talk is about, as I said, robust optimization, and we'll start first of all introducing the single period robust portfolio optimization, which is really the sort of bread and butter of the investment and portfolios, and then extend it to multi-period robust optimization and look at several possible alternatives, and to ensure that we can cover as much material as possible. Robustness is about ensuring survival and given a set of rival future scenarios, including possibly disaster scenarios, but not necessarily only disaster scenarios. In the case of multi-period optimization, this is important from the point of view of transaction costs and rebalancing and incorporating in liquidity conditions. Okay, in order to introduce robustness, I've chosen one example, not really from finance, but from economics. And this is how I entered the area of robustness nearly 30 years ago. At that time, I was working for a research project on the application of optimization techniques to macroeconomic policy, and we had the problem of choosing between different models that one could use to design macroeconomic policy on. And there was in this case, I have named the two that we use in this exercise. One of them is the Treasury model, and the other one is the National Institute model. There is no. I mean, these models are a few hundred equations, linear or nonlinear difference equations, with pretty much another few hundred identities or equality constraints, as you can imagine. And it is quite impossible to invalidate one of these models in favor of the other using statistical techniques. So what one needs to do is to somehow take into account both models, or as many models as there may be, into the calculation, and to try and ensure that the resulting policy takes into account the effects from all the models. In this case, as I said, we had two models, so what we tried to do is to combine the two models together. The combination, and this is stylized, that we can express each model with respect to using a criterion function or a performance criterion. But this is just a stylized description of this. The real optimization is quite complicated, but if you could imagine that we have an optimization problem that takes into account all the effects that are described by the Treasury model, and the same for the National Institute model, and try and see if we can devise a policy based on the monetary policy, for example, based on a combination of the two models. Okay? This lambda is the combination factor. You change lambda from between 0 and 1, you can get different policies, of course. If you look at this problem from the point of view of one of these models, say lambda equals 1, then you base your policy entirely on the Treasury model, and that would correspond to this point in here. Okay? It is also where the objective function or the performance criterion takes the value in here. Now, this is fine if the Treasury model actually turns out to represent the economy, but if it isn't, and that the National Institute model turns out to represent the economy, your performance deteriorates to this point. Similarly, if you base your policy on the National Institute model, and you arrive at this point in the objective function, and it turns out that the Treasury model represents the economy, your performance deteriorates again. So by combining these two, we sort of try and hedge against basing the policy on the wrong model. This orange dotted line is the value of this function as lambda changes, and it represents the lambda times this and 1 minus lambda times this. So basically, if you base your policy on lambda equals 0.2, your object, the Treasury, the National Institute model objective function will give you a value which is corresponds to this point in here, and the corresponding value for the Treasury model will be here. And if you combine the two, you'll get a point on this orange dotted line. So as you change lambda from 0 to 1, of course you could go from fully emphasizing one model to fully emphasizing the other one, ignoring the original one. And this is the point that is at which both objective functions, both criteria, performance criteria are equal to each other. And this is the point in which you really don't care which model represents the economy, because they're both the same, and you have, in a way, taken out the worry of choosing a model, because you have based your decision on the worst case scenario as far as this problem is concerned. This is the point which is the most robust point that can be achieved if you don't have any statistical measure of whether one model is more correct than the other one. And this is really the point that I wanted to come to, is that if you have more than one scenario for the future, then it is possible to combine these in a way that gives you a robust strategy. Okay, there's very little maths in here in the talk, but it's one of those slides in which there is some mathematical formula. The generic optimization problem that we're talking about is minimizing a function with respect to this decision variables, and y is the set of uncertain data vector. Okay, and it may be the particular model that you're using, or as we will see in the finance case, there's much more specific interpretations of this. Okay, there's a specific understanding about the data. Inaccurate forecasts or wrong assumptions about return distribution in finance are clearly two of those. Okay. And of course, disregarding the uncertainty can result in very bad decisions. One of the things that we observe is that we can construct an uncertainty set for the data, the uncertain data, such that any future realization of the data will be within this set with high confidence. Okay, uncertainty sets could be discrete possibilities, and we'll see a number of them very soon. And there can be intervals, in other words, a hypercube, where say between upper and lower bounds of a given realization, is like ranges of forecasts, or ellipsoids. This is the most abstract of them all, but still very useful and very topical. And the robust optimization takes the worst case approach, and it finds the best decision in view of the worst possible scenario chosen among this uncertainty set. Okay, it can be a discrete possibility, it can be an interval, or it can be an ellipsoid, which reflects certain prior knowledge. Okay, if you look at this from a game theory point of view, the decision maker or the investor is choosing to minimize the criterion or maximize the criterion, and the nature is doing the opposite. Okay, in this case, if you're trying to minimize, the nature is assumed to maximize. Okay. And by the way, there is no real problem about minimizing or maximizing. You can multiply a function by -1, and it will be the opposite. Instead of minimizing, we will talk about maximizing. Instead of maximizing, we will talk about minimizing. Another thing, and this is, I think, near the end of the mathematical introduction, and this is a very important point, actually. And the minimax solution, a robust solution, is such that if the x star, the decision variable, is the best you can do from the decision variable point of view, and y star is the worst case that you have identified, okay, or your computation is identified, your the strategy immunizes against any realization of uncertainty y. In other words, the worst case, once you've computed the worst case and your optimal solution corresponding to it, any realization of the worst case in the among the uncertainty set that you've chosen, you're going to be better off. In other words, if you're prepared to design a robust strategy, then any realization of the uncertainty will improve your performance. This is definitional. This is not any statistical assertion. This is just the mathematics. Okay. Now, a few other descriptions. Robustness can be defined in terms of the minimax solution, or robustness can be defined in terms of two concepts. One of them is a saddle point. Okay, as you can see, when you're trying to minimize your criterion function, the nature is trying to maximize in the other direction. Okay, this is a saddle point, a very well-known concept in optimization. And in some of the robust strategies, one searches for this robust solution. And indeed, computationally, this is the most efficient way of approaching robustness. Nevertheless, there are other issues. And this is the other type of worst case. You can see that if you have a function which is x squared plus y squared, the minimum of the function with respect to an x and y is the bottom of the cup here. Okay. However, if you're trying to maximize with respect to y and minimize with respect to x still remains at 0, but there are two maxima. Okay. One of them is minus 2, and the other one is plus 2. And this is supposed to illustrate to you that if you have two or more maxima, the robustness concept will make sure that you are insured against all occurrences of these worst cases. So whether one worst case happens or the other worst case happens, the robustness property applies to all of those worst cases. Okay, and we'll see. Okay, let's come to the Markowitz mean variance optimization and try to apply some of these things to this. Okay, Markowitz aims to find a portfolio with highest expected return and for a given amount of risk. And the optimization model can be described as this one in here, which is the minimization or the maximization, really. You can change the function, but this is formulated in terms of minimization of this, which is the return, but it's a negative of the return actually, and minimization of the risk. So basically, this is the Markowitz model. W is the set of admissible weights, portfolio weights that you can choose, and of course W can be anything that you are used to, including diversification constraints, budget constraints, short selling constraints, and alpha, of course, is the risk aversion parameter, which varies between 0 and 1. When alpha equals 0, you are maximizing the return. When alpha equals 1, you're minimizing risk only. When anything in between is, of course, you're maximizing the return and minimizing risk. Okay, and this is the efficient frontier. You're obviously, almost all of you must know, seen this sort of thing before. This is the frontier that you would get by varying the alpha between 0 and 1. Okay, this is this risk-seeking end, and this is the risk-averse end of the portfolio. any point on this line is an optimal and efficient allocation of the portfolio. Anything above the line is unachievable, unattainable. Anything below it is suboptimal. The mean variance model has practical weaknesses, and of course it relies on correct estimates of the expected returns and correct estimate of the covariance ratios. It also assumes only one possible forecast of the future and outputs an effective optimal portfolio when this is realized. So basically it works with one scenario only. When this forecasted scenario is not realized, this is most often the case, another scenario materializes, the calculated portfolio could perform extremely badly. Okay, we have an illustration. We have two scenarios, scenario 1 and scenario 2, and these are the corresponding efficient frontiers. This is the one corresponding to scenario 1. So, what happens if you base your optimal strategy, your investment strategy on scenario 1, and scenario 2 turns out to be the case, and vice versa? That's the next two slides. Okay, scenario 1 optimal. And if scenario 2 is realized, and if you have chosen your portfolio weights based on this scenario, then your performance will deteriorate to this line. So as you can see, there's substantial decrease. Okay, and if scenario 2 you choose your portfolio based on scenario 2 and scenario 1 is realized, you can see that that too is at best at the same level, and at worst, of course, it too deteriorates. Okay, basically, this is the robust optimal or minimax optimal, which takes both scenarios together and calculates an optimal allocation and the worst case scenario simultaneously. When we say worst case scenario simultaneously, it means that we're not calculating one optimization and calculating a second optimization and doing something in between, but the optimization takes into account both scenarios and tries to and comes up with a single solution, and that's the robust solution. This is it. One can show very easily that this too is a robust. This too is a efficient frontier. Okay. So, what happens if you apply the robust strategy and scenario 1 is realized? Okay. And as you can see, the non-inferiority property that I tried to describe earlier meant that if you're prepared for the worst case, you design your strategy against in view of the worst case, and some other scenario happens, then you're guaranteed to be better off. And this is the case, that if scenario 1 is realized and the minimax optimal is you've applied, from here to here you will be better off, and from then on it will be the same as the minimax strategy. And the same is also can be seen for if scenario. Sorry, maybe I should have. If scenario 2 is unrealized, on the other hand, we're always on this line, the red line. So basically, we're not going to lose anything. This can be contrasted, for example, by what you stand to lose if you apply your scenario optimal strategy corresponding to scenario 1 and scenario 2 is realized. You can see that you're avoiding by applying the minimax strategy from going anywhere below this red line. The red line is the guaranteed return. You will not be falling below the red line if you apply the minimax strategy. And the same also is true, the same graph is also true for scenario 2. If you apply the scenario 2 optimal strategy and scenario 1 you realize, you end up here. This I showed as well, but as I said, with the minimax, you're only guaranteed to be on this line or above it. Okay, now what's the price paid by robustness? I mean, obviously you're paying something for this, this is scenario 1 optimal, and this is the minimax. And when scenario 1 is realized, your performance is this, okay? And you apply the minimax strategy. However, when scenario 2 is realized and you have applied the scenario 1 strategy, you end up in this. So you're avoiding this sort of deterioration, by choosing a strategy that will be here, that will be on this red line, or above it. So basically, if you apply the scenario, if you apply the minimax strategy weights to scenario 1, your performance will improve and you will go nearer to the optimal strategy of scenario 1 only. Whereas if you choose to use on the scenario 1 only in terms of deciding on your strategy, you may end up far below the robust line. Well, okay. What happens when we introduce, and this doesn't only apply to 2 scenarios. In order to illustrate this, we also introduced a third scenario, which is just another one of scenario for the given assets, and this is the minimax strategy, and this is the mean balance frontier for based on scenario 3 only, and this is the minimax performance if you choose the scenario minimax weights, and scenario 3 happens to be materializes, while at the same time, if scenario you base yourself to your decision on scenario 3 and one of the other 2 scenarios are realized, you may find yourself in this position. So there's always a deterioration of performance if you base yourself against the wrong scenario, except when you choose the robust strategy. By the way, Paul, where are you? Paul, I forgot to say that if anyone wants to ask any questions, they can ask anytime they like.
Feel free to ask questions.
Okay, and the single period optimization can successfully immunize against uncertainty when faced with rival discrete forecasts. And there are many extensions of this to that one can discuss. One of them is not discrete scenarios, but continuous ranges of scenarios of, say, for expected returns or the covariance matrices, in fact. Quite difficult problem in the case of covariance matrices, but there are solutions to these. Instead of using variance as a risk measure, one can also alternatively use value at risk or conditional value at risk. And one can immunize against uncertainty about the underlying distribution. In other words, you do worst case bar. Okay, now we go to multi-period portfolio optimization. As we said, the multi-period is important when if you need to take into account transaction costs, as most of the time one would need to, and rebalancing and illiquidity constraints. So basically, this is the inflation and GDP forecast of we lifted from the Bank of England some time ago. It just shows what the purpose of this is. It's merely to show to you that one sees forecasts in terms of values and probabilities, and a discrete, not necessarily discrete, multiple time period intervals. As the forecast changes, and the probabilities change, and as time progresses. And this can be captured in terms of by using a scenario tree. Okay. Scenario tree is sort of a discretized version of reality, it's that reality in the future. So basically, if you are at this point in any period of time, you would have, for example, 3 different return scenarios ahead of in front of you for the next period. You may well have more than 3, of course, or in fact you may want to consider a multi-stage problem where you would have the different returns and different probabilities and of course different branching structures. This is a sort of description, a stylized version of a scenario tree. Most of the time scenario trees end up with very large numbers of scenarios and the computational issues associated with them are non-trivial. Well, scenario tree generation is a very specialized area where one takes into account growth rates, the covariances, higher order moments, and devises branching structures or scenario trees, and manipulating the return values and the branching probabilities. One wants to actually come up with the best forecast for the future. Okay. Okay. Now a little bit of terminology in here. This is a scenario tree. The Ni is the intermediate nodes, set of intermediate nodes, and T is the terminal nodes, which increases the number of scenarios at the end. And AE is the ancestor of node E. In other words, if this is E, the ancestor of E is here. This sort of gives you a flavor of how this actually works. And it is possible to then write the expected wealth at the terminal point of the scenario tree by writing down again the mean variance. This is a multi-stage mean variance representation. You can write down the mean, expected mean of the portfolio, and expected variance at the terminal node. Okay. Given all these probabilities and given all these scenarios. Okay. Just to give you a flavor again, so there are this multi-stage problem. You initially fix the budget and then make sure that whatever you buy and whatever you sell at any intermediate period is financed by whatever you sell. And there are transaction constraints, basically, and this is for the initial transaction, and for any subsequent periods, the wealth that currently in your hands, or the portfolio weights currently in your hands, are given by whatever you made in your previous investment, previous node, ancestor node, plus whatever you bought and whatever you sell, in terms, also taking into account the transaction costs, define what your portfolio weights will be. Then you can calculate easily what your wealth will be. Okay, and expected wealth is something to do with the probabilities and the weights, and the expected variance similar. Okay, now this was done quite a number of years ago, and we have in the since then considered the possibility of having rival representations of the future. Okay, so basically it's a rival scenario trees. In other words, rival discretizations to ensure that we can capture as much as possible what is likely to happen. And again, robust optimization can immunize against the uncertainty of which scenario tree to choose. I can give you an example. For example, if you're using different, if you're evaluating the scenario tree through some sort of simulation, random simulation procedure, different seeds that you use your random generator will give you different scenario trees. That's one thing. Of course, there are many other less trivial reasons why you would consider rival scenario trees. Okay. So the robust optimization with multi-stage optimization, it would then mean that we would consider the best decision, portfolio decision, in view of the worst case scenario tree. Okay, and now as opposed to variance or minimization of the variance of the portfolio, one can also consider minimization of VAR. The alpha VAR is the expected loss with alpha % probability, or C VAR, which is the average loss greater than or equal to alpha VAR. C VAR is the preferred measure in this respect, since it's a convex function which can be optimized efficiently. Okay. There's some backtesting in here, which a comparison between mean variance and C-VAR. This is to do with 20 stocks from the FTSE, and it's comparison between optimizing C-VAR and mean variance. And we found that this is the FTSE as plotted, and this is the equally weighted index, which is quite difficult to beat. And mean variance portfolio is this red one, which doesn't do that well, at least in this exercise, compared to the equally weighted, but the mean C-VAR does the best. And this encouraged us to check out the optimization of worst case multi-stage C-VAR. What worst case C-VAR is that for any given portfolio allocation and for different K scenario trees, K different representations of the future, you would try and compute the maximum over all the Ks. Now, this is the worst case for given case scenario trees. And the robust solution to the worst case CVAR is you optimize your decision in your portfolio. In other words, you manipulate your decision variables in such a way that you will minimize the worst case CVAR. Okay, I mean this. I think we're nearing the very end of the talk now, and this is an illustration of the non-inferiority property of the minimax. In this, the efficient frontier, which is the mean CVAR frontier, is given by this blue line here, and all the others are the robust portfolio weights evaluated using the different scenarios. And as you can see, you can only go above the blue line and never below it because of the non-inferiority property of the robustness. Okay, and this is let's see. This is the mean. We took one of the scenario trees for an illustration. This is the mean variance frontier based on one of the scenario trees, which happens to be scenario 3, and then evaluated the performance of the optimal strategy given the scenario 3 mean variance weights when other scenarios occur. Okay. The blue one is the one that is the robust strategy, and the red one, the green one, all the others, in other words, are below the robust strategy. So basically, if you base yourself on scenario 3, and scenario 3 actually happens, you will be on one of these points on this efficient frontier. But if some other scenario happens, you will be here, and you will be below the blue line, and the blue line is the robust strategy. Yeah, this explains how we took 20 largest companies of the FTSE and generated multiple scenario trees, and then we executed the CVAR optimization or the scenario trees, multiplication, and track out the sample performance of optimal initial portfolio allocations. And we compare the. Anyway, this is the backtesting. Auto sample always backtesting of robust CVAR versus other constraints. This is the FTSE is this purple line here. Equally weighted is just about the green line. The blue one is the best single scenario tree. Okay. And the red one is the robust. So it unquestionably always dominates the performance. Okay, some conclusions. Financial optimization problems require data forecasts, and of course that creates a problem. Because none of these are accurate, and therefore not taking into account of this can lead to catastrophic results. And the robust optimization methodology ensures that we avoid the ill effects of uncertainty and to the best of our abilities, and price of robustness is very often justified, and we lose something, but the price that we pay can always be measured, and most of the time, in fact all the times that we have tested, the price of robustness was comparatively smaller than the catastrophe that one would face. And robust solutions have non-inferiority property, which is what I've been talking about. And of course, the last point is that we mentioned robustness and we mentioned uncertainty and we mentioned scenarios, but there's always a way of defining the uncertainty set that would require some wisdom. And that is really the key to a successful specification of a problem. Thank you.
I'm going to be proactive now and say if there are any questions, now's a good time to ask.
No? You didn't ask any questions, no?
In your multi-period portfolio optimization thing, I noticed the trees coming up, and that necessarily gives rise to the thought that we're actually dealing with something that's going to, in terms of computation complexity, expand exponentially.
Yes.
With a number of time periods. So perhaps you'd like to just gloss over the sort of techniques for reducing the tree to some sort of manageable size, because otherwise it will just crush it.
No, actually, the way ahead for this is not really reducing the size of the decision theoretically, but other ways of characterizing uncertainty. Decision rules that take into account the uncertainties and generate robust rules for choosing your policy is the only way ahead for this. But I have also to say that optimization with large-scale scenario trees is a well-recognized area where there are many, not many, but quite a number of software packages available to do this.
I have a question. You spoke quite a lot about scenario. If you, for example, you take the SEVAR case. In the SEVAR case, as an input, you have like expected returns, the variance matrix, and a few other things. But how do you, in a way, you need, for having scenario, you need a sort of distribution of probability on the different expected returns or whatever. I mean, how do you compute that? What is your model to
Are you talking about the uncertainty in the distributions themselves?
Yeah, themselves. Because if I had to do that, I know how to compute the CVAR, but I don't know how to compute different scenarios on the CVAR because I don't know what model I can put on the expected return.
Yes, there are ways of doing this. Perhaps we should talk about it later on, because there are many ways of, not many ways, but there are ways of incorporating the uncertainty of the CVAR or injecting robustness into the problem. But they're not really, I didn't talk about them and there isn't enough time to.
Can you give a few examples? Can you give a few examples of the ways that you would use to...
Examples of?
Yeah, of the sort of randomization you are putting in the CVAR computation.
Randomization of the CVAR computation.
Yeah, I mean, if you are doing scenario, you are trying to randomize. Because usually what you would do is basically compute historical expected returns and historical covariance matrix
Yes.
to get a CVAR.
Yes.
If you want to do scenarios, you need to have a probabilistic model to model the expected returns and the covariance matrix.
Yes.
So to me, it's randomization. Do you have an example to give, or how do you do that? Or it's secret?
No, I don't think it's a secret. As far as I remember, this was done using the scenario trees were generated by a software that really is not really geared to CVAR at all. You calculate the CVAR given the scenario tree.
Yeah, okay.
Okay.
How do you get this?
How do you get the scenario tree? You get the scenario tree by several ways. One of them is moment matching, which it isn't the way that this was done, but we can actually do moment matching. In other words, we optimize the implied moments of the scenario tree and match them with the observed moments of history plus some growth of the mean. Okay? And we optimize the first 4 moments and co-moments. That's one thing. The other one is the simulations. We tried Monte Carlo simulations. It wasn't very good. We tried homothetic, several possibilities, but the one that worked very well was Sobol sequences. Using Sobol sequences to randomize the data, and then we use clustering to cluster at every stage.
Are there any other questions? Any other questions?
Just have one point that concerns your last point on the conclusion about incorporating wisdom into.
I didn't say incorporate wisdom. I said without there's no substitute. None of these. None of these. Well, perhaps it means that, but yeah, go on.
But I mean, obviously, an alternative approach that's gained some sort of popularity in the literature is the Bayesian approach, where you essentially nominate or you choose Bayesian priors, and then presumably those Bayesian priors are based on sort of a priori information. How can that approach be used in combination with your optimization methodology, or is it really something that's very separate?
No, actually, Bayesians would think that it is something quite separate, but we don't. We wouldn't mind to incorporate the best information available. I'm not sure what you are intending. You are thinking of in terms of incorporating Bayesian beliefs in this. Are we talking about the probabilities, the priors?
Yeah.
Yeah, I mean, there is no harm. But we don't believe that you can actually exactly specify, however Bayesian you are or however non-Bayesian you are, these probabilities. So basically, there will always be some sort of uncertainty there that we need to make things robust with respect to. Whether and if the data is generated through some Bayesian belief, that's fine, no problem. But there will always be some uncertainty around the Bayesian or non-Bayesian specification of the data. Our approach really tries to, and frankly, this is not just us, but there are many people in the world working on robustness. Our approach, at any rate, is to try and immunize the decision to the uncertainties there. I mean, if you look at the way that you have specified a certain probability several times, and if you have a way of actually measuring it in reality sometime in the future, there will always be a difference between them. Okay. For example, this is something that bothers us because and that really needs to be taken into account to actually make the decision as robust as it can be to any inaccuracy that you're injecting into the problem.
May I ask a very basic question? When you mentioned backtesting, I think you mentioned it's out of sample. I think I just missed. I mean, what exactly is out of sample? I mean, are you calibrating anything in sample?
No. You can't. If you're doing this, you go back in history.
Yeah.
Say on 5 years, couple of years, and then you tune the system as if you would tune it today.
What exactly did you tune the?
Well, I mean, basically you have to generate the scenario tree. Okay, the scenario tree has to be generated by using past data. Yes, okay. Past data.
So it's
past data, past the 5 years that we're talking about. So basically 5 plus 10 years of data. You need 5 years of data, for example, to generate your scenario tree, and you want to test another 5 years after that, how effective this thing is. So you go back in history, you just evaluate your scenario tree, and then calculate your decision on the basis of whatever the technique is.
So scenario trees were generated using a historical method. Yeah.
Yes, but hang on. You go ahead and calculate, say you have a 5 period problem. You calculate the 5 period solution and then implement the first period, okay, and assume that you're implementing. At the end of the first period, then you look at the data in the past and see whether you made money or not.
Yeah.
Okay, that is reality. Okay.